Okay, just give me a thumbs up when my screen is visible to all of you. Anyone?
Yes, sir, it is visible.
Yeah, okay. Thank you. Good morning, everyone, and thanks for joining this session on the end term revision session for the deep learning practice. And agenda of this session is basically to cover the basics of week 9 to week 12, go through the slides, understand the concepts, and thereafter we see the only PYQ which is available for this course. Certain things I want to emphasize here, like in the live session, the course instructor has given some hints that the majority of the questions, they will come on the same pattern like the PYQ. And if you have seen the PYQ, then you will find that most of the questions are directly based on the concepts which are given in the slides. And I must confess that I had not gone through the slides earlier. Yesterday only I started, and the slides are really very good. They cover all the concepts. So with this, I will start. Okay. So basically, the week 9 to week 12 is all about vision and what are the different vision tasks which are available in this domain. And one by one, we have taken those tasks from week 9 to week 12. So week 9 started with the basics here, that what are the type of information which can be extracted out from an image. So these are two types. One is semantic. Semantic means what kind of object is there, object classification, localization, segmentation, and or tracking. And the second type of information is metric. Metric means we are getting some information which has got some value. So the metric tasks are like depth estimation or the construction of sculptures or construction of some buildings, taking the view from different angles. Now there are certain challenges in this image tasks. These challenges, they include that there may be viewpoint variations, there may be changes in the illumination, different scales, deformation of the images, occlusion. Occlusion means that something is getting obstructed by some other object. Then background clutter, and last is the motion. So these I'm covering just from the objective point of view. There is a multiple answer question if it comes, so just we refresh ourselves. And focus in the course has been image pre-processing, object recognition, object detection, and estimation of depth from single image. So object recognition was covered in week 9, detection was done in week 10, estimation of depth from single image was done in week 11, and image pre-processing was done in week 12. So before I start this, I will just cover certain basics of the CNN, because CNN is the one which is used in majority of the vision tasks. So a CNN model, a simple CNN model, all of us, we have done the deep learning course. So I will just cover only basics only. Filters, which are also known as kernels. We apply these filters. I will just explain how they're applied. We get an output. Then we applied a pooling layer. Pooling layer can be a max pooling layer, or it can be a average pooling layer, or it can be a min pooling layer. And we then apply some activation functions like ReLU, YOLO, or something, and then we keep on going. So these are the blocks of a CNN. And finally, when we get the final output, we flatten it. So flatten means that whatever is there, for example, we have got a size of here 6 into 6, and there are 32 like this. So we flatten this into 6 into 6 into 32 into a single array, and then we connect it to a fully connected layer, and then we have got an output. So generally in the CNN, you will see that majority of the things are classification tasks. So for the classification task, we use softmax. And I will cover certain, I think somebody is trying to enter a permission. Okay, please come. Okay, so now I will give you an example that there is an input of an image. The size is, for example, 128 by 128, and it is an RGB image, so it has got depth of 3. And we apply, for example, 32 filters on this. So why we are applying these 32 filters? Because by different filter, we will get different semantic information from various portions of this image. So the formula that what will be the output size is given by output is equal to input plus 2 into padding minus filter size divided by 2. Take the floor of this and plus 1. So in this, for example, if I have applied a filter, I'm just taking 5 by 5 filter. I'm saying stride is equal to 2 and padding is equal to 1. So what is the meaning of stride and padding? I'll just cover in a few minutes. So this is your input. This is 128 into 128. So it will have 128 values here, 128 here. So padding means, padding of 1 means I apply 1 more padding all around. And stride means stride of 2, that this 5 by 5 filter which is there, so it will be applied on a 5 into 5 window here. And thereafter, I take 1 slide. So instead of, for example, if it was a slide of 1 and there is a filter of 2 by 2, so first I will do here, second I will do here. But for a stride of 2, I will jump from here, take a stride, and I come here. I hope this basic is clear to all of you.
Yes.
Okay. Okay. So this formula is important because in the PYQs also and in the PS also, the questions they have been asked about this, that the padding has been given, filter size has been given, and we have to find the output. Just remember this important point, that we have to take the flow, which was the incorrect answer in the PA. So these are the basics of the CNN. And the max pool means, max means if I have got a of 2 into 2, so max means that I will apply this here on 2 into 2, and whatever the maximum value is there, it will give the output. Similarly, min will give the min. Average means we take the average. That is good. Now with this, I will go to the week 9 image. They had covered the image recognition, various models which are there. So we have to just understand the basic things about those models so that we are ready for the quiz part only. Okay. So object recognition, what do we do? How do we do this? That we have got a CNN, we give an input, and then we train it on a classification task. So y is your true y which is there. We are getting one y hat, we get a loss. Then we back propagate that loss to update the filter values. So there have been different models with the different sizes of the CNN layers. So this was the first one. These are certain ones which have been given, and these are the winners of that. So the best model till now has been ResNet. Thereafter the Google Net, then VGG, VGG16, VGG19, and then the AlexNet. So we will just see quickly the architectures of these models: LeNet, AlexNet, VGG1619, Google Net, and ResNet. So LeNet is that the convolution filter size was 5 into 5, applied at a stride of 1. And thereafter, the subsampling pooling layers were 2 into 2, applied at a stride 2. So when you increase the stride, so stride is in denominator, so your output size automatically decreases. And the architecture is convolution, pooling, and then fully connected. There are 2 fully connected layers which are given here. Then we come to the next one, which is AlexNet. So AlexNet is architecture is given here. We have got first convolution layer, which is 96 11 into 11 filter. So filter size is very big, but the stride is 4. Padding is 0. So we have got convolution max norm. So just from the examination point of view, remember that LXNet has got a normalization also. So remember convolution max norm, then again convolution max norm, then we have got 3 convolution layers, then 1 max pool layer, and there are 3 fully connected layers. Now maximum parameters, always remember, in a convolution layer will be in the first convolution layer and thereafter the last fully connected layers. So majority of the numbers of the parameters, they are coming from these 2 parts of your model. Any question on this, anyone?
No questions.
Okay, so just we have to remember that normalization is there in the LXNet. LXNet has got CMN, then C to power 3, then we have got a max pool, and there are 3 fully connected layers. Just to remember for one day, for tomorrow. Okay, certain notes on the LXNet that the first filter size was 11 into 11. And due to this, the number of parameters, they increase too much. So coming to the number of parameters, how do we calculate number of parameters? I will just cover it here only in the CNN. So this is your input size. For example, this is 128 into 128, and this is 3. And we apply a filter of 5 into 5 and 32, and so what will be the number of parameters? Can somebody tell me in this?
Be 5 into 5 into 3 into 32.
5 into 5 into 3 into 32. Thanks, Vivek. Thank you so much. So this depth which is there, so this 5 into 5 which is there, it is assumed that this filter which is there, it is 5 into 5 into 3. And we are applying 32 such filters. So output will be, whatever the output size we get, output will be output size, and this will be now 32. This is 32.
We can add,
and now we
also,
apply, for example, any pooling layer. So pooling layer, remember, pooling layer does not have any parameter. No parameter. Okay. So in the LXNet, what has happened? This 5 into 5 we are taking, it is 11 into 11, due to which your parameters, they have a much larger value. Okay.
Sorry, I forgot to add, there will be a 32 bias also in that. If we take bias, then we can plus 32 will be the bias also.
Yes, yes. Okay. So that is the LXNet. The first filter is of...
One question.
Yes,
in this exam subject computations, are they including bias or are they excluding? Has anybody checked?
In one question I saw they included that.
They included
I
that.
guess they mentioned when you are.
So if we see our experience from the deep learning and large language model, generally they tell in the question whether bias is there or bias is not there.
Yeah, in the question which I saw in the, I think it was in the BA, if I'm correct. So in that question also it was mentioned that we have to include the bias.
Yes.
Okay.
Okay. So we have seen the LENet and we have seen the LXNet. Now we come to the different. Now we come to the VGGNet. So VGGNet has 2 parts, VGG16 and VGG19. It denotes the number of layers in both. So VGG16 has got 16 to 19 layers in comparison to LXNet, which had 8 layers. And there are only 3 into 3 convolution, stride 1, pad 1. So the number of parameters are in this part are lesser than the LXNet, and its performance is better than the LXNet in the various competitions. And what they have done, they have stacked these 3 into 3 convolution filters which are there, and effectively they give by doing this stacking, they give the same result as of 1 7 into 7 convolution layer. So what has happened, the number of parameters have reduced, but we have got the same result as we are applying 7 into 7. filter. So it is deeper, and we have got more non-linearities in this, and fewer parameters. So these are certain architectures of this. So just we have to remember the number of layers. So number of layers in VGG 16 is 16. In 19 it is 19. LXNet we had only 8 layers. But in the VGG what we have done, instead of a larger filter, we have got 3 into 3 filter, but we have stacked again those filters. So if we see an architecture like this, for example, you see here, so these are the filters which are there. And if we see the stack, then we can immediately recognize that this is a VGG model. And like I had mentioned earlier, that most of the memory and the most of the requirement parameters are in the first convolution layers, and thereafter in the fully connected layer. So in the VGG, by doing this stacking, they have decreased the number of parameters in this convolution layers. So it has got CCP. So there is no normalization. Again, I have one hint that in the LXNet normalization was there. In VGG, there is no normalization. So we have got 2 convolutions, 1 pool, 2 convolutions, 1 pool. Then 3 convolutions, 1 pool. So these are the stacking. So these are the 3 convolution layers which are getting stacked up.
I had
this
one
is the
doubt
hint
here.
for VGG 16 and 19.
Yeah. So when we say VGG 16 or VGG 19, or when we say that AlexNet has 8 layers, we only count the number of convolution layers and the fully collected layer.
No.
Right.
So this total layers which are there, for example, if you count, these are the total number of layers.
If we will count all the convolution layers and fully connected, that equates to, I think, 16.
Yeah, wherever you have a parameter, wherever you have a learnable parameter, that's a layer that should be counted.
Yeah, so we exclude the pooling layer.
Yes.
Yeah, pooling we exclude.
Yeah.
And somewhere if they are showing a ReLU and all those things also to be excluded. Wherever you have a learnable parameters, that should we call as a layer here.
Yeah.
Thank you, Ravneet.
Yeah. See, one
Okay.
simple heuristic,
So VGG
and
they
these
have just
images are a bit misleading because when I looked elsewhere on the internet, these are not correct. One simple heuristic you can look at that between the LayNet and AlexNet, the beginning part is similar. And between AlexNet and VGG, that end part is similar. You know that layer number 6, 7, 8, which is the fully connected layers at the end, they are present in AlexNet as well as these VGG, both of them. You know, they've got the same structure towards the end. And on the entry side, the LayNet and AlexNet have similar kind of structure. They both have a single convolution and then another single convolution, and then the rest of the network starts. So these pictures are actually wrong. I don't know how do we handle it, but from the real stuff which is there on the internet, these pictures are wrong.
okay. Thank you, Ravneet. I will connect through my.
And you can easily, you know, memorize those things because VGC 16 has got 16 things, and the last 3 layers are fully connected. So that means you're left with the 13 convolution layers. Similarly for VGG 19 also, you're left with only 16 convolution layers. And there are stacks of 3s and 4s, and rest of them are stacks of 2s. So that way you can easily compute it on the fly also. Just, yes, you know, memorize it, because in VGC 16 and 19, both the cases, the beginning and the end is same. It is only the in between. You have got stacks of 3 or stacks of 4. That's the only thing which is changing.
Yes, sir. So all these, nets have got 3 fully connected layers in the end. So after excluding those, we can count the number of convolution layers.
Yeah. So Alex and VG have got this commonality of 3 full. They both have got 4096, 4096, and then the 1000. That 1000 is linked to the number of classes that you are trying to predict. So that's a simple thing you can look at. And in fact, even if you look at the 4096, that also typically coming from that 256 into 4 into 4, those kind of things. So some of those numbers, you know, you can easily compute and figure out what is just above or below that particular layer.
Yes, sir.
Okay. Thank you, Lavlinji. So like Laviji has mentioned, okay, you can see the difference between VGG 16 and 19 in the starting, till here, till the stacking of 3 layers, both are same. Thereafter, there is a difference of here, there are 3 layers stacked, there are 4 layers stacked, 3 and 4. Rest, okay, classification head also remains the same. That is the only difference. Okay.
And as I said, this is a wrong one, because if you look at this one, VGG 19, you got 6 in the bottom and then another 8, that makes it 14 plus 3 is 17. This does not add up to 19. Okay, these pictures are wrong. So don't go by these pictures. Find out something else on the internet. These are completely wrong pictures.
Even the AlexNet net is wrong, because in the end
Yeah,
it
this is
should have
wrong.
three convolution layers, right?
No, in AlexNet, you should have one convolution max in the beginning, and then second convolution max in the beginning, and then 3 in the middle, and then you have got 3 at the end.
Yeah.
So that's what is wrong over. So that's what I said. The LeNet and Alex have got identical beginnings. Conf, that's a common thing between LeNet and Alex, and then at the end, similarity is there with the AlexNet and VGG architecture.
Right.
Yeah. And AlexNet has got a normalization, which is not there in the LeNet and the VGG net. Okay. So shall we go ahead? Okay. So now we come to Google Net. So Google Net has got something unique, which is known as an inception module. And so it is due to the efficiency of this inception module, it has got very less number of parameters. In fact, it is 12 times lesser than AlexNet, but the performance is better than the VGG net. So this is the Google Net. They are applying 1-to-1 convolutions. So I'll skip this. So wherever we come to know that this, then we can identify that this is a Google Net. So it has got an inception module. And the last.
So one thing to remember in the inception module is that the convolution layers here are in the parallel. They are parallelly located.
Yes. And this is the only model where we are using 1-to-1 convolution. Till now, we have not seen any 1-to-1 convolution.
Yes, sir.
Okay. And then we come to ResNet. ResNet has got the maximum number of layers, 152 layers for the image net, and it has got. And then this is the one which is having the skip connections also. So ResNet, till now we have not seen the skip connection. So it is nothing but adding the residual. And in one of the only one PYQ which is available, there is a question on this to identify where this skip connection has been correctly implemented. So this is the correct implementation, that whatever the input is going and whatever the output is there, you take X from here and you add this X here. This we had seen in the LLM also and in the deep learning also. Okay, so we can see significant differences between all these 5 models, by which we can easily recognize that which model. So first LeNet, okay, it has got only 8 layers, convolution max, and then fully connected. Then we came to the next one, which was AlexNet. AlexNet had convolution max, and it had a different something called normalization. So normalization, it happens in AlexNet. Then we came to VGG, where we are stacking the convolution layers. So VGG 16 is there, 19 is there. Then we came to Google, where Google Net, where for the first time we are using 1-to-1 convolution. So that is the only model where we are using 1-to-1. And then we came to ResNet, where we are using the skip connections. So these are certain things which are differentiating these models. So if you remember this thumb rules, then we can identify those models. Is it okay with everyone?
Yes.
So this we have finished. Okay, so from here, okay, I will go to my document. Okay, so we have seen CNN models, and I will just. Okay, so now the CNN, it is a multi-level neural network. It has got 2 constraints. It has got local connectivity and parameter sharing. So there has been a question in the PA also, in the PYQ also. So remember this, the features of CNN. CNN has got local connectivity and parameter sharing. Parameter sharing also and weight sharing also. And what happens that if there is a CNN, for example, this is a fully connected neural network, there is an output 9, input 9, output 3. So number of parameters is 27. But what happens in a CNN, it happens similar to this, that we have got 7 inputs, 3 outputs, but here we are local connectivity. We are not connecting everything. We are just connecting this k is equal to 3. K is equal to 3 means that every output is getting connected to 3 inputs. So by this, now number of parameters, they become k into n, where n is the number of input, sorry. Therefore, the number of parameters, they decrease to 9. So there is a tremendous decrease in the parameters due to this philosophy. Then the parameter sharing, for example, here you have got different parameters, all the weights, weight 1 to 9. But if all weight 1 to weight 3 are shared, then your number of parameters and the requirement of the memory, it decreases tremendously. So CNN has got local connectivity, parameter sharing, and weight sharing also. This formula I have covered. Then image recognition we have seen. Now we come to the week 10, which was about object detection. So in the object detection, what it was covered, that how it is done. So, and what are the various models which are available. So we have got RCNN, fast RCNN, faster RCNN, and YOLO. But before that, we start how it can be done. So what happens, we have got an image and we slide the windows, and by sliding the windows, now we identify that there is some object there. So we make a bounding box to all objects in the image. So this is how it is done. We slide this window, we see there is no cat, then we slide again, and wherever we find, we say ki, yes, cat is there, and this is the bounding box. This is the basic working initial one. Now, the RCNN is a region-based CNN. Now, problem is that if we take an image, then there will be too many positions and there are too many scales to test. So if your classifier is fast, you can do that. But if it is not fast, then we cannot do that. So the solution was that look at tiny subsets of the positions and choose them wisely. So for example, here, just give me a minute. It's a pause. Hi, Seema. नहीं कार्ड तो कोई गायब नहीं होगा मेरे ब्राउन पर्स में था इसमें. Okay, sorry, I had a call. Am I audible?
Yes.
Okay. So we came to that instead of checking for the entire object, we have to look at only the tiny subset of the positions and choose them wisely. So for example, we are looking only towards eyes, this mouth, the flowers. So the slow RCNN, how it works. First of all, the slow RCNN, we can make out about the model that this is the only model which use the support vector machine, SVMs, and then it does the bounding box like a regression. So anywhere we see the SVM, we can know that is the basic RCNN model. So how it worked, we have got an input image, and then we extract the region proposals, which are of a size of around 2000. And then we compute the CNN features on these extracted regions. And then we find whether the object is there or not, classifier. So there is an aeroplane or there is a person. So we are classifying these regions. So on the right side, if you can see, the image is there. So we make extract three regions of the size of around 2000. And each region is passed through one convolution net. So every region has got their own convolution net. And on top of that, we have got support vector machines. SVMs are there. And then we have got bounding box regression. So this will be slow because we are passing three regions, or depending on the size, the number of regions also can increase. So number of your convolution nets, they can increase. And then on top of that, we are doing three operations of SVMs and bound box regression. So this is the architecture of a slow RCNN. Lavlinji, any additional input on this?
नहीं कंटिन्यू करो इसमें वैसे भी ज्यादा कुछ
हाँ so only thing to identify or to differentiate from all the models is this SVM. So wherever if you see SVM, then you know that it is a RCNN, slow RCNN. Now in the faster RCNN, what happened? Now we have got the regions of interest, that are regions of interest from a proposal method. So in the fast RCNN, the entire input image is passed through one convolution net first. Then we find the regions of interest, that is the ROIs, and then we have got the proposal method. And then they are passed to fully connected layer. And then we do the linear and softmax classifier and the linear regression for the bounding box. So the key difference here is that first we are passing the entire image through one convolution net. Then we have got the regions of interest with the proposal method. And then we do the pooling of this. So ROI is available in this. Then we do pool, pass through the fully connected layer. And from fully connected layer, one goes to the classifier and then another goes to the linear. So instead of having three here, we are having only one. And the concept of ROI and the proposal method has come into fast RCNN. So it has got unique features. What? First convolution layer is there. Then we have got ROI. Then we have got proposal. Then we pull it, pass it through fully connected, and then use softmax classifier and the linear regression. So have you understood the difference between both again?
Yes.
Okay. Now, without so these are certain differences between RCNN and fast RCNN. The slow RCNN is very slow. It takes around 47 seconds per image, whereas the fast RCNN takes around 2 seconds per image. In the training in RCNN, it is multi-stage and slow, whereas in the fast RCNN, it is single stage end-to-end. Similarly, memory-wise, fast RCNN, no such storage is required to store the features. But still, your speed is very low, which is 2 seconds per image. So with this, we come to faster RCNN. Now, faster RCNN concept is that we pass the image through the CNN. Again, we have got the regional proposal net. So we have got the proposals. And this feature map, which is there, it passes to the ROI pooling also. So when we are passing through the regional proposal, one we are passing directly to the ROI pooling, and we extract the features. So in the faster RCNN, the unique feature is this regional proposal network, RPN. So this is the RPN. Anywhere we see, we can say that it is a faster RCNN. And what is this RPN? RPN is a fully convolution layer. It is trained end-to-end, and it shares the convolution feature maps with the detection network. Okay, and with this, your time, the efficiency increases, your time per image decreases to 198 milliseconds. And there is a mask RCNN also, which has not been covered in our syllabus. And it just adds instance segmentation on top of the faster RCNN. Now we come to some points from the practical side here, that what are the hyperparameters in faster RCNN. So we got this RPNs which are there. They got anchor points and the anchor scales. So we can tune these hyperparameters anchor scales Anchor scales is nothing but it is the size of anchor box. Can be 128, 256, 512, and anchor aspect ratio. That what is the ratio by which you want to increase. So this is the architecture of faster RCNN. We have got a convolution layer, then we have got region proposal network, then we have got the ROI pooling, and then we have got the class bounding and the box and the mask. Now with this, we have seen slower RCNN, we have seen fast RCNN, we have seen faster RCNN, and we have seen the different unique features by which they can be differentiated. Is that okay? Can we move to YOLO?
Yes.
Yes.
Okay. Now we move to YOLO. So YOLO means that you look only once. So what it does, when the image is passed, the entire image is split into S cells. For example, here it has been divided into 7 cells. And for each cell, you generate some number of bounding boxes, for example, 2 or 3. And for each bounding box, there are 5 predictions: X, Y, W, H, and the confidence. Confidence says the presence of the object or not. What is the confidence? And then for each cell, we also do the object classification. So when we train it, we have got X, Y, W, H, confidence and object classification for the image against which I'm training. And then we train this model. So this is an example that this is the cell, and in one cell, we have got 2 bounding boxes. So this bounding box will give me X, Y, W, H, and the confidence. And in this cell, total cell, I know that there is a car. So I have got the classifier also, and against this, I train this. So for all cells, we will have 49 number of cells. We have got 98 boxes, and each box is giving these 5 parameters. And then for each cell, I have got the classification also, that what is available in this. Okay, so this is the YOLO architecture. It has got 24 convolution layers. Input image size is 448 into 448. That is standard. So whatever the input you give, the YOLO fits that size. So it does a resize to 448 into 448 into 3. There are 24 convolution layers. These are the default parameters. And output is this of size 7 into 7 into 5 into 2 plus 20. 7 into 7 into 30. This is for YOLO 5. So each cell is predicting X, Y, W, and H, one confidence value, and some number of class probabilities. So these 6 things, they come out of the YOLO. Now this YOLO loss function has been asked many times. So this is the architecture of one cells. You see there are 2 boxes. So these 2 boxes, they are giving X, Y, W, and H. And this probability, the confidence which is there, it is nothing but the probability of object. And this box is also giving the same thing. And on top, this is the classification. So this is the P bird by object. If object is available, then what is the probability of bird, probability of cat? So these are the from the cell which you are getting. Loss function gives first of all the loss of the coordinates of X, Y, W, and H. Thereafter, this probability of confidence which is there, the confidence, it includes the no object also and the object also. And thereafter, it takes the classification also, whether it is correctly classifying or not classifying. So from here only we can take the hints. It takes coordinates X, Y, W, and H. It takes this probability of object. Then it takes the probability of no object and the probability of the classification. Is that okay? These 4 or 5 things? Because they have been asked in the PA also, and they have been asked in the PYQ also. Okay. Okay. So what are the main hyperparameters in YOLO training? Main hyperparameters are image size, depth multiple, which is scaling the model depth. Width multiple is scaling the model width. NC means number of classes. Anchors, predefined anchor boxes. So I think it is not required and it has not been used also. And how to use YOLO, we have seen in our GA, I think it was GA 10 we had done. So most of us, we have used the YOLO. So YOLO needs your data set in a particular format. So it has to have X, Y, W, H, has to have confidence and the classification. So all these things are to be available. And on top of that, you can train a YOLO model. Is that okay?
Yes.
Okay. So then I will skip this. Train YOLO and all that. Okay, so now comes the important part here, all these classifications. So MAP, precision, recall, and all that. So I will cover in the these basics of precision, recall, and all that. So we come to a confusion matrix first. Confusion matrix means that what was actual and what was predicted. So actual was 1, this was 0, this was 1, this is 0. So if it was 1 and it has been predicted as 1, this is known as true positive. If it was 0, or you can take it as -1 also, -1. So if what it was -1 has been identified as -1, it is true negative. Now, this was actual -1, but it has been identified or classified as positive. So it will be what again? It will be false positive. Is that okay?
Yes.
And if it was actually 1, but it has been identified as -1, so it is false negative. Okay. Now, take the definitions of precision and recall. Precision means that out of total how many have been identified positive, how many are actual positive. So this is true positive divided by true positive with false positive. So if you forget this also, you just remember this, that precision is always in this direction. You have identified these many as positive and only this is a true positive. So precision is true positive plus false positive. Recall is that out of how many actual positives, how many have been correctly classified, identified as positive. So this is total number of positives and how many have been identified as true positive. So this will be true positive divided by true positive plus false negative. So your recall is in this vertical direction, if you forget the formula also. And then F1 score is nothing, is equal to 2 into precision into recall divided by precision plus recall. Is that okay?
Yes.
Okay. So these are the basics. Now we come to MAP. That is the mean average precision. So mean average precision, how do we do? That with every step, you calculate the precision. So first image has come. You have, for example, out of 5, you have identified 4 images correctly. There were total 5. So you get a true positive is equal to 4. There is no false positive is equal to 0. False positive out of 4. So here you calculate the precision at this stage. So precision is this much. You come to second, next 5 come, you have identified 3. So your next precision is this. Third stage, you get so many images, you have identified this correctly. This is your precision. So this your MAP is nothing. MAP is the mean of these precisions. So you get these values, you add these values and divided by the number. Is that okay? Is this correct, Lavinji?
I think one change. Sorry, please.
Yeah.
So what I thought was it is first done class-wise. So
Yes.
your average precision is for every class. Then mean is across classes.
Yes.
Mean
Yes.
average precision.
Yes. Yes. You're right. So you're doing this for one class, second class, third class, and then you take the mean. But I'm just covering from this image point of view that how this box comes and how we identify.
See, there are two things here. We have a
Yeah.
mean and then we have got average.
Yeah.
Okay. So in general, we compute the precision by looking at multiple predictions. Okay. So when we compute the precision, we are computing it for looking at multiple predictions of a class. So precision itself is involving multiple predictions. Okay. So in this case for MAP, what they're looking at is that you are varying these thresholds, and for different thresholds, your precision and recall will change. So as you vary the thresholds, how your precision and recall is changing for a single class, that gives you the average precision by varying that threshold. So unlike a plain vanilla case where we just compute a precision, here we are varying, like for different values of recall, how does the precision change? Okay, so this is the first level of averaging is done. Once this is done, then afterwards it is a simple mean of all of those things. So this first step is a little bit tricky. In the question that was being shared in the WhatsApp group, I believe some information was missing because they did not mention about the thresholds. They just gave the scores.
Yes. Yes.
Okay, so we have to, the first average precision, how to compute that, that is a part everybody needs to look at carefully, because that involves changing something and computing multiple precision values for the same class and then averaging all those precision values. So typically you're changing the thresholds, because if the threshold of IOU is 0.5, you get a certain precision. If the threshold is 0.7, you will get a different precision. Okay, so you can get different kind of precisions. So that multiple precisions for a single class, this is something we are not normally dealing with. Normally we just have one precision for a single class. Over here, you have to first compute multiple precisions for the single class, compute the average, and then take a mean across the classes. Unfortunately, there is no example with all these computations available. I'll see if tonight I get some time today evening.
Yeah.
So I have two questions in this, if I may.
Yeah.
Vivek, so can we see this question when we go to that question? So I think with that things will become clear.
Okay.
So no, Vivek, ask. You want to ask something?
Okay. So like you said, Lavi, that this you're varying the recall to get the precision within the class. So does that amount to varying the recall? I think would be akin to varying the thresholds only. So that is my first question.
Yeah, it is all dependent on the threshold only.
Okay. So
it is all,
right.
Something has to change, only then recall will change.
Yeah. So one is varying the recalls and getting the precision within the class. One is varying the thresholds and getting the precisions within the class. So I was not exactly. So I thought
both are same because recall can be changed only by varying the threshold only.
Got it.
Okay. So the reason I mentioned that thing is because when you look at all those illustrations, they have got a graph where on the horizontal axis you have got recall and on the vertical axis you have got precision.
Right.
So in that graph, the interpretation is as you're changing the recall, how the precision is changing.
Okay. So my second, got that. Thanks so much. So my second question is, so average, what do you do? Do you take the area under the curve is by integrating the average precision, or how do you average it? Or do you just, because
that is how they normally mention, but for our purpose, we cannot do that integration thing. We don't have that, function available. So typically what you can do, you can make some slices. You can create some kind of bins that the, IOU value 0.1 to 0.3 and 0.3 to 0.6 and 0.62. So that can give you, some easy way of doing those computations. But all these things, there's nothing like that is mentioned in the lectures. And they have not even given any kind of solution for this thing. So we need to first find out some mechanism through which answer is matching. So far, we were all saying that answer is wrong. I believe answer is coming out wrong because we are just taking there are two averages to be done here. One is the average, another is a mean. We're doing only mean. We're not doing the
Right.
averaging of precisions.
Thank you. Thank you.
Yeah. Okay. So this precision F1 score are covered. So these are the slides okay, which
Yeah,
Vivek
Shah,
was
this is
mentioning.
the illustration. If you look here,
Yeah.
horizontal axis is the recoil and vertical is the precision here.
Generally, if we see our earlier lectures in the DL, it used to be like this. This used to be the area.
Yeah, that was purpose was different. There you were doing that ROC AOC thing. Over here, that's how the people plot it. Okay, because in DL and other places they're doing that receiver operating characteristic. That's a mechanism where they draw it like this. But the key thing over here is that your recall and precision, there is always, both these numbers are changing with each other, and then for a given class, what are the various kind of precision values which are possible? That's what we're trying to figure out. For a given class, what are the various precisions which are possible? And then take an average. That will give you the first part of average precisions. Okay, this is a part which we need to figure out what is the right way of doing it, because we cannot do the integration. So typically taking these strips and doing some kind of bins and then computing it, something like that, we'll have to figure out.
Yeah. Okay. So Vivek, okay, it has been covered here. What you are saying, that is correct. So average precision is calculated for each class. And after calculating for each class, then mean average precision is simply the mean of the AP values across all the object classes.
Right.
Yeah. Okay. So this I have covered. This is the implementation of faster RCNN. So we have to see only the parts, okay, how to identify faster RCNN. So it will have an ROI cooler. It will have,
I think one thing that everybody should look at is the definition of all these architectures. That class which is modeling that particular architecture. Everyone should go familiar with that code, because I've seen some snippets which are giving us little bit of code and saying whether it is a AlexNet or whether it is something else. So just by looking at those code little bit snippets of the class definition,
Yep.
They may be asking us to figure out which kind of architecture it is.
So some important questions from week 9. For an RGB image with dimension 300 into 300 from a mobile phone, how many parameters would need to be handled by a traditional MLP? So this question itself, it is incorrect because they have given only the input layer. They have not given the hidden layer. So number of parameters will be here. So in the answer, what they have given, they have just given the number of inputs, 300 into 300 into 3, 27, 2,70,000. Okay, features of CNN, we saw parameter sharing, local connectivity, and the weight sharing. Then consider a 4 into 4 input matrix. What will be the output matrix after applying an average pooling with a stride of 1? So whatever the pooling is there, the formula remains same. Output is equal to input plus 2p minus f divided by s. So you will get an answer to that. Mark the gates which are not solvable by normal perceptron. So normal is this one. This cannot be solved. This is plus. This is plus. This is minus. This is minus. So by a normal perceptron, we cannot distinguish, and this is a X1 OR gate. Then for a CNN network with 10 input nodes.
Sorry, where can you get the definition of NOR and NOR gates? Like this is back in DLP1, right? Starting off deep learning perceptron.
Yes.
You can get it on internet.
Yes.
You
Yes.
have OR, and negation
yeah.
of OR is an OR. You have got AND, negation of AND is an AND. Okay, and exclusive NOR. You can find these are very standard terms. You can get them on internet.
Yeah, I think we have covered this in deep learning.
Yeah, deep learning week 1 itself, it was covered.
Yeah, that's
so
what.
Yes.
So whatever OR is coming, your OR is coming, just do the inversion of OR, you get the XOR, NOR. Similarly, whatever AND is coming, you do the inversion of that, you get that. Okay? Is that okay?
Works.
Okay. Yeah. Okay. Now we come to for a CNN network with 10 input nodes and 5 output nodes with a local connectivity of 3 nodes. What do you think should be the runtime and storage requirements without parameter sharing? So this is related to this. There are 10 input, 5 output, and k is equal to 3. So this is 3 local. And formula for number of operations or the number of parameters is equal to k into n 15. Just give me a minute. Hi सीमा, हाँ मेरी कॉल चल रही है सीमा.
This quiz 3 has only 15% weightage. So unless you are in deep mess, maybe you use this time to get the concept of all these things rather than focusing on your exam marks. Well, once we are out of the course, generally we stop studying about it. Okay. And this mean average precision is good to understand how to do it, but then if you don't do it, maybe you lose 5 marks, 5% marks. So be choosy about how do you want to spend your time today. There might be some other course which can give you a better return on investment. Has anyone done the week 12?
I have gone through it. Did a few of them. Read through its notes. So yeah, covered that.
Is
I haven't watched the lectures, but only gone through the slides.
Yeah, I have gone through the lectures, all the week, 9, 10, 11, 12.
Does it make any difference if you go through the lectures or not?
Uh,
Video.
I think slides is enough.
yeah,
The only risk is sometimes I wonder that whatever is there in the slide, is it really part of the lecture or not, or am I studying something extra? That's the only question sometimes come, because there's a lot of stuff in some of those slides. And to what level, because on each slide you can write a complete book also. Some of those are so much in detail. So how much time did the professor spend on it? This is one small tool which has been on my list to make for last 2 years, that for any video and looking at the slides, what is the number of seconds or minutes spent by professor on each of those topics, and then figure out how much we should study it. Because if they're spending only 30 seconds on one complex slide, does not make sense for us to study too much on that one. Sorry, Ritik, you were saying something.
Yes, sir. I was saying that there's one useful tool called Notebook LM. So through that you can summarize any YouTube video and you can make notes. It gives us summarized notes of whatever.
No, I'm not
is-
asking for summary. I'm asking for how much time was spent on each topic.
Yes. Sir.
Like how much time was spent. If the professor is spending 5 minutes on a topic, or 15 minutes, or just 30 seconds.
Yeah, that is useful.
that
But how
gives
do
us-
you how do you calculate that without watching the videos?
writing a program to do that thing? I'm not going to watch the videos. I'm saying this is a pending project for me, that to write a small Python script which can go through that whole stuff.
Mhm.
actually,
Conclude it.
this thing, in YouTube, these things are already implemented. If you
Actually,
watch,
if you use the Whispers transcription thing,
Mhm.
that can be very effectively used for this thing. Because
That's
it is
an
giving you
interesting
the
project, sir.
it is giving you the timestamp as well as the
Mhm.
text. So that could be a very, very effective way of doing things.
Yeah, that's an interesting one.
In fact, there are a lot of professional tools which are used in the call center and all these places for this kind of audio analytics. they do a lot of this kind of stuff, like which topic was discussed for how long between a customer and a call center agent. And, they do a lot of this kind of analytics.
But the tricky part here is how do you analyze that what slide is taking how much time?
No, that's you can easily do with that whisper thing, because it is giving you the text, the spoken text, as well as the timestamp.
But you need to decode what is written in that slide, and then you have to provide that so that whisper can decode.
No, whisper can take a speech
Mm-hmm.
into text and
Mm-hmm.
give you the timestamp of each dialogue.
Okay.
This was part of the DLP.
Very
Yeah.
great. Lalit sir,
Sir,
you are
you're not audible, sir.
Okay, am I audible now?
Yes.
yes sir. Yes.
Okay, okay. So can we go ahead with these questions? Sorry, I had a call.
No problem.
Yeah. Okay. So question number 7 is the formula k into n, which we had discussed earlier. So your number of parameters, they become number of this 5 output nodes and into 3 nodes. So every output node is getting connected to 3 nodes. So 5 into 3, 15. So your runtime is 15 operations and your storage is also 15 parameters.
How are we
The
calculating
same question,
storage?
if we say with parameter sharing, then it will become only k.
Only k. So in fact, the next question is same here. So I will just draw it here. So the concept is like this, that these are the 5 outputs and you have got 10 inputs. And k is equal to 3. K is equal to 3 means that every output is getting connected to only 3 inputs. It's like this, something like this. So this is 5 and this is 3. So 5 into 3, 15. And here the parameters are not shared. So you have got P1, P2 up to P15. Okay. If your parameters are shared, it means P1, P2, P3 will be shared at all places. Then your number of parameters will become 3. Is that okay?
Yeah.
Okay. But your number of operations will remain the same. Kn is equal to 15. So here in the next question they have given that the same output, same input, k is equal to 3. What do you think should be the runtime and storage requirement? So runtime will remain same, 5 into 3 operations. But your storage requirement is for the parameters. So you are sharing only the 3 parameters. Okay.
So that storage part is not clear. Can you draw the architecture of the second question in which storage is 3?
So storage is what do you store? You store the P1, P2, P3, na?
Yeah.
So what is your requirement? Okay, you will have only 3 storage.
Okay.
Okay. Earlier you were storing P15, so your storage was 15.
Okay. Yeah.
Okay. Now we come to ReLU. So why is the ReLU preferred over the sigmoid activation? This we have seen in DL also and LLM also. So if you see, all are applicable. ReLU is computationally cheaper because it is straight away linear, no computation of the e-values. ReLU helps mitigate the vanishing gradient problem. Sigmoid outputs are bounded between 0 and 1, which can limit learning in a deeper network. ReLU introduces sparsity in activation because whatever is less than 0, everything becomes 0. So lots of sparsity comes. Okay. Then is the next question. For a CNN layer, suppose the output after the convolution and pooling operation is a feature map of 16, 16, 32. Height is this. If this feature map is flattened and connected to a fully connected layer with 128 output nodes, how many parameters, weights, and biases will this layer have? So the answer is incorrect in the answer key. If you calculate the number of parameters with biases, so when you flatten, so it becomes 16 into 16 into 32. So this is your flattened layer. You connect it to 128, and if you consider the bias also, so it will become 16 into 16 into 32 into 128 plus 128. So if you calculate, you get 1048704. However, in the answer key, the answer they have given without bias, which is 1048576. So that is a discrepancy in this question. Is this calculation understood by everyone? How we have calculated? Any question on this by anyone?
No, sir.
Okay, good. Okay, then in CNN, why is the softmax activation function typically used in the output layer? So basically, they have given the answer that to ensure that the outputs of the CNNs represent probabilities that sum to 1 across all classes. However, if you see the first also, this also looks correct only to convert the output feature maps into class probabilities. This is also correct, Lavlinji, as per my understanding.
No, we should not use that one.
Okay.
Because your feature map will never be run through the. See, if you look at the CNN, the part of a convolution network is just to extract the features and nothing else. CNN alone will never be used. It is just extracting the features. Once you have extracted the features, then you put something on top of it. That may be a classification head, that may be a regression head, that may be something else. So you are always putting something on top of it. So this classification head is where the softmax is used. Okay. So the feature map is never going to be converted into the probabilities. It is always the output of the fully connected, which will be converted into the softmax.
Yeah. Okay. Thank you. Okay. We go to question number 12. What is the primary distinction between the feature learning layers, convolution and pooling layers, and the classification layers fully connected? So Lavlinji just now he has explained it in detail. So your convolution and pooling layers, they just do the feature, they extract the spatial and hierarchical features, whereas the classification layer, they map these features to specific output categories. These are the roles of both. Now we come to a calculation part. Consider a CNN layer, input size is given, filter size is given, number of filters has been given, stride is given, padding is given. What will be the output size of the feature? So output size is always, we find the output. So you will get from here. So 32 plus 2 minus 5 divided by 2 plus 1. You take the flooring of this. So 29 by 2 floor will become 14. Then you take 15. This answer is also incorrect in the answer key. And the output size now will become 15 into 15 into number of filters. So like I had covered in the basics of CNN, you have got this output and that is the number of filters which you have applied. Okay. Now next one is you are given an image of dimension 227 into 227 into 3 representing its height, width and color channels. You want to flatten it into a 1D array using Python. Which of the following code snippets will correctly achieve this transformation? So image.flatten, this is a function which achieves the flattening. Similarly, image.reshape -1, it converts to 1D vector. This also achieves the same thing. And if you use image.reshape double bracket and you give the size 227 into 227 into 3, this also achieves the same. And these two functions are same. -1, -1, and the full size. The code is the same, functionality is the same. But if you give image.flatten and 227, this is incorrect. And similar question has been asked in the PYQ also. So please have thorough understanding of these three functions. Is that okay? You can try it out in your Colab or Jupyter notebook and you will come to know. Now,
Actually, with reshape, you have to be careful when you're giving -1, when you're giving a count, the effect has different actually. It is not always same. Okay. Yeah.
Okay. In a CNN, parameter sharing ensures that same set of weights is applied across different regions of the input, enabling the special feature detector. Consider a 7 into 7 into 3 input image passed through a convolution layer with the following characteristics. 4 filters, kernel size 3 into 3, stat is equal to 1, no padding. Which of the following PyTorch code snippets correctly demonstrate parameter sharing in this convolution layer? So they have given these codes. So we have to understand certain things again in this. This when we pass, for example, conv2d, when we are passing, then automatically your parameters are shared. They have given number of channels correctly, 3. Output channel is 4 because we want output size. Okay, when we are applying, we get 4. And automatically when we do the forward, your parameters are shared. So this is the correct implementation. There is nothing incorrect. Now here, second question, in this, everything remains same, only they have changed the padding is equal to 1. So if you see the question, what they have given, then the answer is incorrect. But in the answer key, they have given that still parameter sharing is done. But if you see from this point of view, then it is not the correct implementation. In the third code, what they are doing, the same code is there, padding is equal to 0. However, here now we are doing manual. We are defining the weights and the biases, and still it is doing the same conv2d, and still parameters are being shared. In the last part, only the last code which is there, they have changed it to n and conv3d. So when we use conv3d, it expects an input of shape 5. So due to this is incorrect. Okay.
This is a PYQ or is it a PA?
It is a PA.
Okay.
Okay, then next question, for the given code snippet, what will be the output? What is the output shape? So output shape, okay, you have to check that input shape is 6 into 6. And from here, you can check this input channel is 1. Input channel is 1 means that this is 6 into 6 and the depth is 1. The out channel is also 1. So output channel also we get 1. Kernel size is 3. So we get the F is equal to 3. Stride is 1, 1, both horizontal and vertical. So stride is 1. Padding is 0. So you apply this in the formula and you get the answer. So your output will be now 1 into 4 into 4. So your output will be 4, 4, and 1. Okay. Now, if, for example, if they had mentioned here out channels is equal to 3, then your output size would have become 4 into 4 into 3. Just from the understanding point of view. Okay, now we come, if the padding is changed to padding is equal to same, what happens next? So padding is equal to same is used when you want the same output size as the input size. So this is your input and this is your output. The size should be same. So then accordingly in this formula, you put output is equal to input plus 2p minus f by s plus 1. You put output is equal to input, the same values, and you can calculate that what will be the padding value for this. So to achieve this, a padding is applied. Okay, so this is the functionality of padding is equal to same. Now we come to next question, custom pooling operation with a pool size of 2 into 2, stride of 2 into 2 using PyTorch. The input is this. Now here, this is important. This question has been asked in the PYQ also. That what will this code achieve? So in this code, there is a minor tweak only, that this f.max pool td, it gives the maximum value. But whenever you pass input as minus input, so here they have passed as minus input, it will always give the minimum. It will become min pool. Is this okay?
Got it.
Okay.
Actually, it negates all the values of which are map uh, negative, and then you take minimum of it.
Yes. Okay. It converts everything to negative, and whatever is the largest in that, it takes
Yeah.
that value. So automatically it becomes your lowest value.
And to convert that negative back to the positive, I think that before that max pool 2D, we do a negation of f also.
Yes. So just remember this only, that okay, to have min pool, you pass okay, input as a minus input. Okay. Now we come to next question here. They have given input. Input is 8 by 8. And
One question in the previous.
yes.
Why you have taken value of p as 1? Because padding is not given, right?
Padding, I have taken 0. If padding is not given, then padding is 0.
Yeah. So this 2 into p should be 0 then, right?
So it is 0, no? This is I, this is F.
Okay. That is it.
Okay.
So both, just to interrupt, sorry, both minus, usually minus f dot max pool do you do inside minus input, only then it's min pool, or if it's only minus input, then also it's max pool.
So what is happening? What is happening actually? And somebody had explained just now that you have got, for example, 1, 3, 4, 9. So by this minus input, you are converting to minus, and now you are applying a max on this. So what will be the max on this? -1 is the maximum value, and by doing this minus f, now you are converting to +1. Is that okay?
Got it.
Okay. So then similar question is there on this calculation. So from the calculation point of view, please remember this formula. It will fetch you at least 5 to 6 marks. Okay. +1 and take the floor. This is an important formula. Okay. Input channels, output channels, kernel size, stride, padding is equal to 0. Okay. So this is the one. Now, in this question, they have asked that what is something wrong in this code. So I will just share this code full. Okay. So they have started with a deep neural network. First, a linear they have defined 100 into 128. So it means your input is 100 and the hidden layer is 128. Then you have applied sigmoid on that. Then 128, 64, it means this is 64. Again, you have applied sigmoid on this. Then 64, 32, then we have got 32. Again, we have applied sigmoid in this. Then 32 into 1, so this is 1. And again, they have applied sigmoid on this. So this entire architecture can be seen like this. So what is something wrong about it? The wrong is that when you are applying the sigmoid, we know the characteristic of sigmoid. That is, it becomes y hat into 1 minus y hat when we are doing the back propagation, the loss value which is there, it contains this value. So at every point of time, your loss is vanishing. So it will suffer from the vanishing gradient problem. So this is the problem with this architecture. Is that okay? In the deep learning also, this concept was covered. And that is the reason where we start using ReLU, GeLU, and all variants of ReLUs. Okay. So the next question is, we have been given some tensor and they have given these data points. These are the data points, and if you see, this is a XNOR. And they have said that you train this model, a simple MLP. So in a simple MLP, we have got only input and one output. So we know that a simple MLP will not be able to distinguish between the XNOR. So what is the final output will look like? So these are the 4 points, and your classification will look like something like, and they have given this round function. So it will never converge. It will not be able to distinguish between all points. So if your final will come something like 0.5, 0.5, 0.5, 0.5. Okay, so this was the basic essence of this. Now we come to week 10 questions where they have asked, for example, given an image data set for object detection, how would you pre-process the fast RCNN? Consider the following code snippet. So they have given the resizing, they have given HOG features are there and generate proposals, and they have generated proposals. So what is the part which is not a part of fast RCNN? So in the fast RCNN, we know that we have to do the resizing, we have to generate the regional proposals, we have to classify each region proposal directly. But this part, which is HOG, means histogram of oriented gradients, this is not used in faster RCNN. This was used to be prevalent in the old CV models which were there. So this is not used in this. So just remember that HOG is not the part of fast RCNN. Now, which of the following statement correctly differentiate between fast RCNN from YOLO? So see, fast RCNN is a single stage detector while YOLO is a two-stage detector. This is not true. This is opposite. YOLO is a single stage, whereas the fast RCNN is a two-stage. Second is fast RCNN relies on external region proposals, whereas YOLO divides the image into grid for detection. We have seen this. This is true. Third, YOLO uses selective search for region proposals, while fast RCNN performs end-to-end detection in one step. This is false. This is opposite. This is YOLO, and this is fast RCNN. Both fast RCNN and YOLO perform detection and classification in a single stage. This is no, because fast RCNN it does in two stages, whereas YOLO does in one stage. Okay, now, like I had mentioned earlier, they have given a code and they have asked that what can be the architecture, which is the model. So if we see this model, it is using a SVM classifier. So this is using a SVC. So SVC was used in which architecture? It was used in slow RCNN. So we can identify the model that it is a slow RCNN. Okay, now again they have given a faster RCNN. They have given
one doubt here.
Yeah.
So in both slow and fast RCNN, we use selective search, or is it opposite?
Okay, so I will just tell you the main differences. So in the slow RCNN, what you are doing, you are having this image, you are selecting certain portions and you are passing these portions, and every portion was going to one convolution layer, and thereafter you are applying SVC and the regressor. Is this okay? This is the slow RCNN.
Yes.
Whereas in the faster RCNN, what you are doing, you are passing the entire image through one convolution layer. So there is one convolution layer on top of this. You are passing it through this. Then you have got proposals, region proposals. So from this convolution layer, now you try to make out that where the object is available. So this is the region proposal. Then you pull it. So that was a pooling, that ROI layer. And on top of this, now you are applying only one classifier, which is softmax, and you have got linear regressor. Is this okay?
Yes, sir.
Okay. Yeah. Okay, now we come to faster RCNN. So they have asked that what is the kind of architecture in this. So they have given us RPN layer. So immediately we come to know that where the RPN layer was used. RPN layer is used in the faster RCNN. So immediately you can make out that this is an architect of. So which of the following architectures incorporate this type of regional proposal RPN for object detection? So we know that it is used in faster RCNN. Is that okay? So those small differences which are there in the model, we have to keep that in our mind at least till tomorrow. question tomorrow, maybe afternoon or evening. Okay, after that we can forget. So those small differences which are there, which are differentiating those models, just try to remember that. Is that okay?
Yes.
Okay. Now we come to the next question. So they have given predicted bounding boxes and the confidence scores. So we know that YOLO model, it gives this x1, y1, x2, y2. This is the score. This is the confidence level, whether the object is available in this box or not. So this, it has given 3 boxes. Whereas the ground truth says that there are only 2 boxes where these objects are available. Okay. And then they have given the function to calculate IOU. X1 is equal to max, box 1, 0, box 2, 0, y1, box max again. X2 and y2 are min. Then there is a formula for intersection. Then we find the area for both the boxes. And then we find union is equal to area 1 plus area 2 minus intersection. And then IOU is defined as intersection divided by union, if union is greater than 0. Now, they have given max predictions. So they have given the thresholds, then true positive, false negative we have given. And then for prediction, padding predictions, if max is equal to false, so what we are trying to get, we are trying to get the predictions. We have to calculate the precision and the recall using the precision recall function. And so how do we have to? First prediction, 50, 50, 100, 100, score is 0.9. So is it matching with any box? So yes, it is matching with this box. This is matching with this box. So what happens? It becomes a TP, true positive. Is that okay?
Yes.
Okay. Now we take the second prediction. The second prediction, 30, 30, 70, 70, it matches with this. So this is also true positive. Now we take the third box. Third box is 200, 200, 250, 250. So we know that nothing is available here. So this is a false positive. Is that okay?
Yes.
Okay. So we have got TP is equal to 2, FP is equal to 1. And we have to calculate precision for this positive only. So precision is how many, that out of how many total we have classified as positive, how many are true positive. So that is TP plus divided by TP plus FP. This is 2 by 3. This is 0.67. And recall is that out of how many true positives we have been able to classify correctly. So there were two positives and we have been able to classify both of them correctly. So your recall is 1. So this is the answer, precision and recall.
How would you identify the false negative here? Jose?
Haji?
If they ask you, like, how would you identify which one was the false negative?
There is no false negative here.
Okay,
We have not
but
identified it. Okay.
assumption there was a false negative. How would you identify that false negative?
So false negative, they have given in the code. False negative is the length of the ground truth. So they have already given that is 2.
Okay.
Okay. Yeah. Okay. Now we come to the next question. Next question is the one on which we had the discussion. That again the same question is there, but in this with the bounding box, the classification is also given. So this is a cat, and this is a dog, and this is a cat. The ground truth is this and this. So now I think Vivek, hi Vivek, am I audible?
Yeah, yeah. Hi.
Okay. So I'll request you to kindly contribute, and we will try to apply the same thing which was given in the slide. So see, this is a cat and it has been identified as truly cat. Okay. This is a dog which has been correctly identified as a dog. This has been identified as a cat, but there is no cat. So for cat, there is a true positive is equal to 1, false positive is equal to 1. For dog, true positive is equal to 1, false positive is equal to 0. And they have also must have given false negative value somewhere. This precision recall. So precision for cat will be what? Is equal to 1 by 2.
Right.
Okay. Precision for dog is equal to 1.
Correct.
And this is the only average because we don't have any other value. So your MAP becomes mean average of this. So this will become 1 plus 1 by 2 divided by 2. If we apply that. Lavlinji, any input on this?
So one doubt here, you have to divide by the number of classes or divide by the number of predictions.
No. See the predictions which are there when, for example, if I had for cat, I find the mean precision as I keep on taking the steps. So here we are doing incorrectly. So what happens? First step we find for cat, then cat, then cat, or like Lavlinji had contributed that by changing the IOU values. So by the IOU values when you are changing for a particular class, this will keep on changing precision and recall. So you
Right.
have got, so for that particular class cat, you will take the mean precision. That for all the IOU values which are there, you divide it by those number of values and you add that precision. And similarly you take for dog, and then whatever the precision value is coming, now you add this and divide it by the number of classes.
Okay.
So I think in this question is slightly ambiguous, and we can take it on discourse also, because for having this, okay, we need IOU values and how they are changing. Okay, so I will leave here only instead of confusing everyone. Okay, now we come to the next question. They have given certain steps and they have asked us that what is the architecture, that this code is there, and try to identify the architecture. So how do we do that? So first we see, for example, here is a region proposal, ROI pooling, and there is a fully connected layer for classification and regression. So first this is there. This. So we know that this region proposal and ROI pooling are used in what? Both are used in fast RCNN. So immediately we can say that this is a fast RCNN architecture. Okay, then the next question is about again about the concepts of precision and recall. They have given the predictions, they have given the ground truth, they have given the true positive, true negative, false negative, and then we have to calculate the F score. So given the predictions and the ground truth, what is the calculated F score? So how do we do that? For the true positive, we see that there are how many ones are there, and they have been correctly identified as 1. So 1 is there, 1 is there, 1 is there. So there are total 3. And what is a false negative? That actually it was 1, but it has been identified as 0. So this is 1, 0. This is false negative. So it is 1. True negative means 0 and identified as 0. So 0, 0, 0, 0. So there are 2. False positive, that it was 0 but identified as 1. So 0 and 1, this is the 1. And after once you have calculated this, now you can calculate the precision and recall, and using these values you can find the F1 score. Okay, so next question is about the calculation of IOU. So this is nothing, it is simple, just going through the code. It is just a normal Python code. Just run the Python code and do the calculations, you will get the answer. So there is nothing technical or any twist in this question. So I'll skip this. Anyone facing any difficulty in understanding this question?
No.
Oh, thank you. Yeah. And similar question is there in PYQ also. So please, I can solve this. Very simple. Just you have to follow the code only and keep on doing the calculation. You will get the answer. Okay. Next question is there, that which of the following loss components are included in the YOLO loss function? So they have given this predictions. These are the ground truth. These are the hyperparameters of YOLO. They have given the loss function. They have given a function for the coordinate loss, object loss, no object loss. Then they have given x1, x2, x2, IOU loss, classification loss, and total loss. So see, in this itself, they have given the clue that they are asking which of the following loss components are included in the YOLO loss function illustrated in the code snippet. So in the code snippet, if you see the YOLO function we had seen, so YOLO loss function has got coordinate loss for all x, y, w, and h. Then this IOU loss was not there. Then second was the your confidence loss was there, and confidence loss has got two portions: object loss and no object loss. Third was your classification loss. So all these losses which are there, these are the part of YOLO. Okay, and here okay, they have also included IOU. But if you see the loss function, and somebody has asked correctly on the discourse also that this IOU loss is not the part of YOLO, but in the answer key they have given this as correct. Otherwise, these are the loss values which are included in the YOLO, and it has got four parts: 1, 2, 3, 4. Okay, which of the following networks can be used as feature extractors in the faster RCNN? So in the faster RCNN, you have to use a convolution layer. So first is your convolution. So these are the nets okay, which can be used: VG16, RESTnet, mobile net. This GAN cannot be used. RPN cannot be used. YOLO cannot be used. YOLO is not a feature extractor. So these are the ones which can be used as a feature extractor. Which of the following statements correctly differentiate between a fast RCNN from slow RCNN? So if you go through the statements, the fast RCNN performs feature extraction on the entire image once, whereas the slow RCNN extract features separately for each region proposal. So this we have seen. Okay, so this is the correct statement. Okay, with this we have completed week 9 and 10. Can we take a 2 minutes of break before we go to week 11 and 12?
Yes.
Yeah, thank you. Bhai, can we start?
Yeah.
Yeah, okay. Okay, so week 11 is about depth estimation, that how to find the depth from an image. And first of all, we have to understand what is the meaning of this. So depth estimation is nothing to estimate the pixel level depth relative to the camera position. So, and what are the applications of this? So applications are in autonomous navigation, like in indoor humanoid roads, autonomous cars, in aerial, like drones, in the virtual augmented reality, like virtual meeting rooms, gaming, robotic surgeries, and scene understanding, semantic summarization, large scale 3D mapping, and architecture or heritage capture. So one way of acquiring the depth is using the stereo method, that if we have got the images from two different sites, then we can use that. And how it is done, I'll just explain that this is, we capture an image from this direction. So this is the point, goes here, and then we capture from a different direction from here. So this, for this same point is given. So this is your depth ticker which is taken. So when you are taking the picture from different directions, you are covering the horizontal shift. And using this horizontal shift delta and using the trigonometric relations, then you can find that what is the depth of this. This is about how we do. But in the course, we have been dealing with the monocular depth estimation, means from the single image only. So it is a challenging task because there are no depth cues like parallax, which we get from stereo. There are some cues that exist, are vanishing points, object sizes. They can give some cues to us, but these cues cannot be quantified through a rule-based method. So what are the different tasks in the single image depth estimation method? First is the multi-scale depth deep network. Second is the UNet. They come, both of them, they come under supervised techniques. And the third is the unsupervised, that the depth from left right consistency. And in the course for all these three, the three different models, they have been covered. So this is the UNet has been covered, and the second is the MPR net, and the third one is the unsupervised. So we just have to understand the characteristics of these nets. So the depth map from a single image using multi-scale deep network. So in a multi-scale deep network, it has got two parts. One is a coarse network. It has got a large filter size, and it predicts the overall depth for the scene. And the second is the fine network. So it has got a smaller this, and the input of this coarse network is fed into the fine network, finally concatenated, and we get the refined image. So this is the architecture of this. So understand the various parts, the function of coarse network and the fine network. So coarse network is predicting the overall depth, whereas the fine network is refines the global prediction locally. Okay, so these are certain results. And then we come to the UNet based care. So this UNet has got two parts. It has got one encoder downsampling, then it has got decoder upsampling, and then it has got skip connections. So what is happening in this part encoder, it has got only, if you can see, it has got only the convolution layer. These are the convolution layers, and then the max pool. So it has got two convolution, one max, C2, one max, C2M. And in the decoder, what is happening? It is upsampling. It is, so here if you see, the size is decreasing. Here the size is increasing. That's why it is known as upsampling. And there is no max pool here. No max pool. These are the certain characteristics of the encoder downsampling and the decoder upsampling. And at every stage, there are skip connections. So here, there is a skip connection, there is a skip connection, there is a skip connection. So this is the unit architecture. There are certain questions on this architecture in PYQ also and in the PA also. So just understand the encoder part, okay, what is encoder is doing, what is the decoder upsampling is doing, and what is the function of skip connections. So here I have written what is the encoder downsampling. It is using the convolution layers followed by a max pooling to progressively reduce the spatial dimensions while increasing the number of feature channels. So the depth is increasing by the number of feature channels, but your size is, the dimension is decreasing, spatial dimension. Decoder is doing opposite. It involves transpose convolutions or the unsampling layers to increase the spatial dimensions of feature maps. It combines low-level features from the downsampling path with high-level features to produce detailed output depth maps. And skip connections, we are having residual connections at every stage. The loss functions, some definitions they have given, MSE, MAE, we know that. In this unit, okay, we are using MSE loss. These are certain examples or results of this. Now, third part is the unsupervised one. So in the unsupervised one, we need both images. We have got the left image, and this unsupervised is used for the stereo images. So we have got left-right image pairs. So what do we do? First, we find the disparity in that. So use the left image of the stereo pair, predict the disparity. So we are using the left image and we find the disparity with the right image. Thereafter, we convert this left image to the right image using the predicted disparity. So it is something like this. We have got left image, we have got right image, we find something called disparity, and we convert now this I1 plus D is equal to I dash R, and this is IR. So now we use it as a image against which we deploy our model, we train our model. So though we did not have any Y, true Y, but we have made one, we take the right image as a true Y and you train I dash R on this. So this is the basic functioning. Then they have given a model which is used for this stereo depth estimation is a matching cost CNN. So matching cost CNN, it has got certain, it computes the matching cost based on the CNN feature for image. So we have got a left input image patch, right input patch, and we using the parameters are shared in this, and we compute the matching cost between this. And by training this, we find. Okay, so these are the only parts of this week 10. So what are the important points from week 11? That UNet has got an encoder convolution plus max pool. Decoder, there is no max pool. Loss function is MSE. For unsupervised, we have got again the loss is MSE. Okay, there are certain, these are the questions from the PAs that in depth estimation from stereo image, what is the primary role of the disparity map? So the disparity map which we are doing between IL and IR. So it is nothing, it is doing identify the matching points between the left and right images and measure their displacement. So this is one image, this is second image. First we identify which are the matching points and then we find their displacement, how much they have been displayed. So this gives us the disparity. And using this disparity, we convert this image to I dash L and use this IR for training. That is the part. What are the primary challenges of estimating a depth map from a single image using a multi-scale deep neural network? The first network which was there. So the main challenge is that we don't have any stereo image. So this is a single image. So understanding the global context and handling variations in scene geometry and textureless regions. So these are the challenges. In others, if you see, they have given stereo images, two images, using depth sensor. So they all are used in stereo images. So that's why these three options are incorrect.
I think depth sensors are alternative and not you know
So what
challenges.
using, yes, yeah. Okay. Now, what kind of pooling layer is used in the UNet? So UNet, okay, if you remember, UNet has got a encoder and it is using a max pool. By max pool only, you reduce the size. Okay, so you are using 2 convolution layer, 2C and 1 max pool layer. Here you are just using up sampling, no max pool. So these are the questions. Okay, there were only 7 questions. So just remember these 2-3 finer points which can assist you in the quiz. And now we come to week 12. So week 12 comprises of image pre-processing and majorly 3 tasks: image denoising, image formation model, uh, denoising, super resolution, and deblurring. So these are the 3 tasks which are covered during the lecture. We will see one by one. And they have covered, okay, especially 3 models for that. So we will see the architecture of that. So for denoising, they have given us MPR-NAT, that is a multi-stage progressive image restoration. And the architecture of this map, it has got 3 stages: first stage, second stage, third stage. And there are certain unique features of this MPR-NAT. It has got something called CAB. I will just cover it. This has got SAM. And every stage they are having connected to the next stage, to the SAM. So what is a CAB? CAB is a channel attention block. This is the part of your MPR-NAT. And what it does, it is a I'll just cover it here. So channel attention block is for exploiting the inter-channel relationship of features. So when the input feature is coming, it is going to the max pool also, it is going to the average pool also, and taking from the max, taking from the average. This is the channel attention module, which is a neural network. Again, it gives the max pool and the average pool. And by comparing these both, we find the channel attention. So this is the function of channel attention block. Then we come to SAM. SAM is nothing but it is a supervised attention module. So here we are doing the supervised module which we are doing, and I will just cover it here. So this is introduced between the stages to improve performance in multi-stage image networks. Then it has got the third feature, which is known as CSFF, cross-stage feature fusion. So these are all the parts of your MPR-NAT. And your loss function is this. So it contains ground truth image, edge loss, Charbonnier loss. So these are your loss functions. Just remember here this term that Charbonnier loss is used in the MPR-NAT. Okay, so it is a supervised training. This is a supervised training, MPR-NAT. And MPR-NAT, just remember these important parts. It has got, first of all, 3 stages. In every stage, it has got CAB, it has got SAM. So these are the parts of your MPR. Okay. So these are certain results of MPR-NAT, far better than all models. Then we come to the next, which is the image super resolution. And many of us, we had used this model during our GA11. So they have covered in this super resolution model, which is known as, these are the challenges in SR, that's okay. So the GAN-based approach, which is there, it is a better than MSE-based solution. And if you remember, we had used ESR GAN during our GA11. So this was a variant of this GAN only. So what is a GAN basically? It is a generator and adversarial network. So how does it do? Generator adversarial network, just in the basics, there is a generator, it generates an image. The adversarial, like this discriminator which is there, it says, I'm producing an image, I'm not a fake. Whereas okay, this discriminator which is there, it has got the real image also. So now it compares this with this image and it sends back saying that no, you're not a real image. And by this, when you train this by this loop, finally when you get the image which is there, it is identical to this. So now you can remove this, and using this generator now you can generate the images. So this is the basic functioning of a GAN network, generative adversarial network. This network is quite understanding of this, or the study of this is quite exhaustive and is used in many fields. But I have just covered the basic functioning, how it is functions. So it has got a generator and it has got a discriminator. So it is generating from a low resolution image. It passes through a feature extraction module. It does the upsampling, and then it is the restore. The discriminator, it is doing supervised training. It has got the real image. It tells no, your result is incorrect. It sends back. Again, it regenerates. So finally, what happens when you're training? Finally, your generator which gives, it will start giving you the correct image. SR-GEN is the photorealistic single image super resolution using a generator adversarial network. This is a model. It has got a generator network. It has got a discriminator network. And the loss function, if you remember here, in the SR-GEN or any ER-GEN function models, your loss function is not MSE. Because due to the MSE loss, what was happening that in the image, we were not able to find out the contrast in the edges and all that. Due to this MSE losses, these regions used to be smoothened out, and that's why the result was not accurate. And here we use something called perceptual loss function. So this is the network setup. It uses a generator and a discriminator. Generator generates realistic image, while discriminator tries to distinguish between super resolved and the real images. Already I've covered this. So this is the architecture, and in the generator, parametric ReLU is used. So this is, you can remember, in the generator, and in the discriminator we use ReLU. Okay, so these are the parts of that. And the third function is called image deblurring. And for that, so till now we have studied for denoising MPRNE, for super resolution SR-GEN, and for deblurring is the third model, which is called as a LA-KD NAT. Okay, so LA-KD NAT has got various these blocks which are there, LA-KD blocks which are there. It has also got the skip connections, and it is something in like a U shape. You pass the blurred image through these blocks, and then it gives a sharp image. And it is also a supervised model, so there is a real image here. You are training on that. So there is a loss function by which you are updating your bits. So the architecture is a U-shaped. It has got 4 levels, and all these 4 levels, they have got n LAKD blocks, where n varies from 1 to 4. The input processing takes an image I with dimension h into w to 3, extracts low-level features through an initial convolution layer, passes through the features into an encoder-decoder structure for blur removal, followed by a convolution layer to recover output features. So this is your architecture. So remember, it has got 4 levels. Then it has got LAKD blocks, and initially it is using a convolution layer. Here is a filter. And how one LAKD block looks like. So this is a LAKD block, one block. So you have got a layer norm, you have got depth wise, you are extracting point wise. So these are your levels. So these are 4 levels. And then you are doing layer norm, passing it, you are fusing the pictures, whatever the features you have got, you stack them and take out and give it to the next block. So this is the These are all basics from week 12. So week 11 and week 12 are slightly easy to just understand and to remember. With this, can we quickly jump to the PYQ? There is one PYQ only.
Yes, works. Let's go.
Okay.
Lalit, is
So,
there any distribution of questions across these weeks?
Lavlinji, what I understand from the content of these weeks, so majority of the content is in week 9 and week 10.
Okay.
So I expect that maybe around 60 to 75% questions will come from these 2 weeks.
Okay.
Otherwise, week 11 and week 12 are very easy. Hardly they can ask any question from that. Okay. So now we come to PYQ. So they have asked a question. So all of you, please, you can open the PYQ because I have just cut and pasted this in a haphazardous manner. So they have given, consider the following code snippet for the loading and modifying VGG NAT 16 classification task with 10 classes. Okay, so first take a code they have given like this. Class is VGG 16 modification, number of classes is 10. Super is this. So this is standard step. How do we define a class? Self VGG 16 is VGG 16 pre-trained is equal to true. So this is also correct. Self VGG 16 classifier 6. This is the classifier had is equal to NN linear 4096 and number of classes is equal to 10. So if you see this, this is a correct implementation of VGG 16. So there is nothing incorrect in this. Okay. Then block B is for VGG 19. Again, the same code is there, only they are using VGG 19. So this is also a correct code for VGG 19. Then they have given block C, loading VGG 16 and freezing feature extractor layers. So what they have done, defined VGG 16 for param in VGG 16 model feature parameters. Param required grad is equal to false. Okay, so they have frozen their secure and VGG 16 model classified 6 is equal to NN linear 4096 into 10. So in this also, now in block D, what they have done, VGG 19 with feature extractor, they have defined VGG 19 and they have defined the classifier. So they have not frozen. So they have given certain statements and we have to find which are true. So first they have written block A uses VGG 16 and modifies the classification had to support 10 classes. So we see this is correct. We have passed number of classes equal to 10 and we have passed it to the model. So this is the correct implementation. Second statement is block B and block C both used VCG 19 but differ in how feature extraction layers are handled. So you see here in the block B, here they have defined block VGG 19. They have defined VGG 19, that's okay. And VGG 19 param requires grad is equal to false. So what they have done, they have a block in the block B, it is a different, whereas in block C, we are just entirely freezing. So block B and block C, there is a difference only in the updation of the weights, not in the feature extraction. So this statement is incorrect. In block C, freezes the feature extraction layers in VGG 16 for transfer learning. So this is true. Here we have frozen by making it false. Block D unfreezes feature extraction layers in VGG 19, making it trainable end to end. So see here, we have not frozen anything. So everything is getting trained end to end. So this question is basically from our experience of GAs, how we did our GAs. So by just going through that, we can easily find that which is the correct statement. Is this okay with everyone? Understanding?
And this block B and C feature, how feature extraction layers are handled. Can we just show block B?
See the model which is there, VGG 19. Are we defining any new feature extractor?
No.
In the VGG19 block B
Yeah,
and
see.
block C,
Okay. Okay.
there is
Yeah,
only
yeah.
this difference. Okay.
Yeah. Thanks.
Yeah.
The model is also different. No?
Huh?
In blocks,
Yes, model is also different. This is VG16 and that is VG19. Yeah. So, the given below picture is likely to describe which architecture. So, see, this is not like how many convolution layers and what is the size. So, by seeing this, I myself, I could not identify this as LXNet.
No, the image size or LXNet is always 227, 227 into
Yes, yes. So this is the only hint here. And
We can count the number of layers, I think.
so number of layers is the 5 only.
Also, compared to the other like
Okay.
VGNet and all.
Okay, so
the architecture differs.
eight layers. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay. So these are the hints here. So these along with the size of. Okay. Now, okay. Then there is a question. Suppose I have an image of 227 into 227. Which of the following code snippets correctly implements a min pooling operation with a window size of 2 into 2, stride of 2, and padding of 2? So remember what we had discussed earlier. So it will use -x and -f. So this is the correct one. And rest everything they have not given. Consider a black and white image of 227 into 227, which of the following correctly demonstrates a function to flatten it. So we had seen in our function image.flatten will flatten this, image.reshape -1 flatten it. This -1, what it does, it automatically it finds the size and it flattens it to the 1D vector. Or you pass image.reshape and the size, current size 227 into 227. So these all three are the correct answers for this. And what they have done to make life easier for us, they have given like this, that this will be the output. Image reshape will give this output. This is incorrect. Image flatten will give this output. This is correct. Image dot reshape 227 into 227, it will give this. No, it will not give. Image dot flatten, this is entirely incorrect. So this is incorrect. Next is the which of the following code snippet correctly implements the skip connection in RESTnet. So they have given the codes. So this is the first code. So what you have to do, you have to just come to the forward function and draw how it is passed. So see, there is a x here, and then they have defined residual is equal to x. So this is the residual. They are passing through convolution layer. Then they are doing ReLU. Then convolution, then they are passing through residual. X is equal to x plus residual. So this has come from here and come here, then applied ReLU. So this is the correct implementation of a skip connection or the residual. Whereas here, if you see the second code in the forward, there is no residual. They are just passing convolution, ReLU, convolution, ReLU. So there is no residual, no. In the third, what they have done, they have given residual is equal to self dot convolution 1 of x. So after the convolution, they are doing x, which is an incorrect skip connection. The skip connection is always from x to this point. So that's why this is incorrect. And the last one, again, there is no residual, so this is incorrect. Then next question is, suppose you are implementing a YOLO function with the following classes: dog, cat, car, house. Consider this image, and they have asked, okay, what can be the maximum number of bounding boxes? So maximum number of bounding boxes will be the maximum number of these classes. So if you count, we have got 1 dog, 0 cat, we have got 6 cars in this image, and there are 3 houses. So maximum bounding boxes can be 10 only. Is this okay?
Yes.
Okay. Then we come to next question. The following code snippets represent different blocks in the fast RCNN pipeline. Identify the correct arrangement. So remember the fast RCNN. What was the architecture of fast RCNN? It was passing through one convolution NAND for the feature extraction. There, after that, it was going to region proposal. Then it was going to ROI. And thereafter, it was going to the fully connected layer with the output layer. So this is the architecture of a fast RCNN. And they have given all the blocks here. So we have to just identify. So this is the region proposal. Second, B is the feature extractor. So feature extractor comes first, then region explore. Block C is the ROI cooling, which will come after the region proposal. And the last one, D, is your fully connected head. So your it becomes BACD. Okay. Now, which of the following code snippet correctly models the loss function in YOLO? So this we have seen YOLO, coordinate loss, confidence loss, which includes both object and no object, and the classification loss. So there are 4 losses. So we can see here what are these are the losses. So coordinate loss is there, lambda chord into MSE loss predictions and target value, this 2, which are your X, Y. Then the confidence loss, which is the object loss. No object loss, it is calculating. Classification loss, it is calculating. And then it is calculating total loss. So this is correct. In this, it is coordinate loss, confidence loss, classification loss, but there is no object loss. In this, coordinate loss, confidence loss, class loss, again, no object loss is not there. And then in this only, it is calculating coordinate loss and no object loss. So classification loss is not there. So just remember these losses: coordinate loss, confidence loss, and confidence loss will have 2 parts, object loss and no object loss, and then the classification loss. So it has to have 1, 2, 3, 4 losses. Next question is about precision and recall. So this we can easily calculate. We have discussed this thing in length, so I don't feel any problem in this. Okay. And now, how many convolution layers are there in the original YOLO architecture? So this we have to remember. It has got 24 layers. Okay. Next question is about the calculations. So like I had mentioned earlier, this is a normal Python code. You just go through the code and just you keep on replacing the values, finding the values and calculating, you will get the answer. I will just solve this, for example. This, okay. So here they have given box 1 and box 2. So x1 is maximum of box 1 0 and box 2 0. So it will be maximum of 0 and 1. So x1 is 1. Y1 is max of box 1 1, box 2 1. So maximum of 0 and 1, this is 1. X2 is minimum of box 1 2 and box 2 2. So minimum of 2 and 3 is 2. Y2 is minimum of box 1 3, box 2 3, 2 3, it gets 2. Then intersection is torch dot clamp. Clamp is the one which keeps a value which does not allow value to go below 0. So it has given minimum is equal to 0. So it will not go below 0. Torch clamp x2 minus x1. X2 minus x1 is 2 minus 1, 1. Into torch clamp y2 minus y1. Y2 minus y1 is 1. So your intersection becomes intersection is equal to 1. 1 into 1 is equal to 1. Then calculate area. Area 1, box 1 2 minus box 1 0. So this 2 minus 0 into 2 minus 0 is equal to 4. Area 2 you calculate. Union is area 1 plus area 2 plus minus intersection. 4 plus 4 minus 1, 7. And IOU is an intersection divided by union. So just simple code here. We don't have to do anything. But for the examination point of view, just try to remember the meaning of IOU. IOU is nothing but intersection over union. Okay. Any question on this?
No questions.
Okay. Now, next question: what will be the function output for the given bounding boxes? Now consider the following code snippet used in the multi-scale deep network for single image depth estimation. So this is the depth estimation, the first model before UNet, which we had used. Both blocks play different roles in the network. Which of the following best describes the role of two blocks? So in the multi-scale deep network, we had the depth network also. So what it was doing, the block A was generating high-level global features and outputs and initial codes, depth map. So remember, in this map, we had something called codes and fine. So codes was using large convolution layers it was giving, and then it was giving input to the fine one to produce fine. So if you use the logic, then you can immediately identify that this answer is right. Now, which of the following code snippets correctly implements the downsampling operation in a UNet architecture? So in a UNet, just you remember UNet like this. UNet, there is a encoder downsampling, decoder upsampling, and then there are skip connections. And in the UNet, in the encoder sampling, we have got the convolution nets 2 and 1 max pool. Here we have got only the convolution layers upsampling 1, no max pool. So if you go through the code snippets, immediately you can come to know which is the one which is doing the downsampling. So here it is a convolution layer, max pool. So there are 2 convolution layer, 1 max pool. So this is the correct one. Here it has got only convolution layer and ReLU. There is no max pool, so this is incorrect. Here only pooling is there. There is no convolution layer, so this is incorrect. Here only convolution, no pooling, so this is incorrect. So in the downsampling, both convolution and max pool both are available. That will be the correct code snippet. Is that okay?
Yes.
Okay. Okay. Next, we go to the next question. Consider the following predictions in ground truth. The mean squared error is calculated using one of the following code snippets. Identify the correct implementation and its result. So this is simple. Question is there. Absolute. Okay, this is wrong. Predictions minus target square dot mean. This is the correct. It will give you the correct answer. Predictions minus target square dot sum divided by the prediction size 0. This will also give you the correct answer. Though in the PA, they have given the answer key is incorrect. And in the PYQ also the answer is incorrect. However, on discourse, they have clarified that this answer is also correct. And we can see from the output also, they're giving the same output. Here they are giving only predictions minus target square sum. So this is incorrect, not dividing. So MSE is defined as 1 by n y hat minus y square. This is the formula for MSE. Okay, in a stereo vision system, left-right disparity is used to compute depth by comparing corresponding points in the left and right images. Which of the following statement about left-right disparity is correct? So disparity is the absolute difference in the pixel intensities between left and right images. This is wrong. So recollect this, we are passing from one direction. This we are passing from second direction. And for the same point, when it passes, it estimates the depth. So when the disparity which is there, it is only the horizontal shift which is there between the points. And I had covered earlier also when I was covering this topic. So disparity is the horizontal shift between the corresponding points in the left and right images. How much it has shifted in the horizontal direction. Next question is on the generator and the discriminator. So the generator produces high resolution images from low resolution inputs, while the discriminator distinguishes real high resolution images from generated high resolution images. So remember this, low resolution image goes through generator. It produces a high generator this, The discriminator, it compares it with the real image, and then it tells, no, it is not the correct image. So this loop keeps on happening till the time generator generates the image which is as real as the real image. Which of the following code snippets correctly adds Gaussian noise to an image? So this is a similar question is there in the PA also. Please go through that. So, and the correct answer is that you are passing noise STD is equal to 0.1, and then you are generating a random like image. So random integers will be generated, and then you are multiplying them by the noise STD 0.1. What are the benefits of using depth-wise and point-wise convolutions, as in the depth-wise separable convolutions comparable to standard convolutions? So this question has come from our LAKD blocks, where we used to have 4 levels. We were doing depth-wise also, point-wise also. So they reduce the number of parameters and computational cost when we are doing this. And this has been specifically mentioned in the slide, making the model more efficient. Okay.
One question, which you can
Yeah.
just clear that.
Yeah.
This rand would be like generating Gaussian numbers, right? Between 0 and 1.
Between 0 and 1, yes.
Okay, not integers, right?
Not integers, yes. Random and like. Thanks, Vivek. Okay, so now they have given a generator function. So they had asked us to identify which is the generator, correct generator. Okay, which of the following are common uses cases of super resolution using SRGAN? So this is all logical. You can easily identify. No point in explaining this. Okay, so this was the last question. I have finished. Okay, from my side, anybody wants to give some additional input or any query, I'm ready for discussion, and I'll request everyone to participate. Thank you. Any question from anyone?
Sir, can you explain the architecture of ResNet and the difference between unit skip connection? Like we use a skip connection to pass certain stage input and concatenate while upsampling. But the residual layer in ResNet is something different. So can you distinguish between both of them?
Okay, so I'll tell you, Ayush, the ResNet is a very deep layer network. So the deep layer network always suffers from a problem that the gradients, they might not come till the last layer, and the update of all the weights will not happen. And that is the reason in the ResNet, okay, we use the residual connections so that the gradient passes through all the layers and all the weights are updated.
See, the purpose is different in ResNet or in most of these areas where even in the transformers also, you are adding the residual. Okay, it's a mathematical addition. Whereas in case of UNet, you're not adding them, you're concatenating the inputs. Okay, the purpose in UNet is to reconstruct the image, whereas purpose in other cases is about the vanishing gradients. So you're adding that number. So that's a key difference. On one place, it is a mathematical addition. Other place, it is just a concatenation of data.
Okay.
Any other point from anyone?
So one question regarding this, what Lavleen explained was, so even in an LAKD, it would be a concatenation, or would it be a skip?
It's a concatenation. LAKD.
Okay.
Thanks, Raja.
Okay. So I will just tell you, we have got time here. So I'll request all of you just go through the slides, and majority of the questions, they are from the slides and concepts we have discussed. So with this background, if you will go through the slides, I believe you will have a better understanding of the topic. So with this, I'm very thankful to all of you to join this and to have a such a fruitful discussion and to share each other's knowledge and to fill in the gaps in our understandings, whatever we are having. Thanks a lot, Lablinji. Thank you, Vivek. Thanks, everyone.
Thank you, Lalit.
And yeah,
Thanks,
and wish you all the very best for tomorrow's quiz. So
Thank
bye bye.
you
Have a
so
very
much.
nice day. Bye bye. Take care.
Thank you.
Okay.
Thank you.